The educational talks are actually the highlight, I think, of the meeting, so we can kind of learn. That's always a good idea. And similar to the other speakers, I'm going to be presenting mostly review articles from other groups and myself with just a little bit of data thrown in. So I can skip this slide because the previous speaker has already talked about the importance of nanoparticles for passive targeting using the EPR effect. The benefits of nanoparticle drug delivery, I think, as most of us have already learned, that producing the particles is fairly straightforward, and we can control size and the size distribution. We can either encapsulate or conjugate active drugs or emitting agents to them. The nanoparticles encapsulating the drug protect the drug, and we can deliver drugs that otherwise would not be able to be delivered systemically. The nanoparticles can carry multiple drugs or multiple imaging agents with a large surface area for targeting. This tends to lead to a longer plasma resonance time, and the particles can traverse the cell membrane, which often small molecules can't, and this is particularly important for bypassing the multi-drug resistance. So what would an ideal therapeutic nanoparticle look like? Well, it should selectively and rapidly accumulate in diseased tissue, should report biochemical and morphological characteristics of the area for molecular imaging. It should deliver a therapeutic dose at the same time, and it has to be safe and, of course, biodegradable. So here we see a schematic of a polymer particle that might have drug either incorporated into it or attached to it, imaging agents that could either be incorporated on the inside or attached to the outside. The imaging could be for MRI, could be for optical, could be for PET spec. If it's conjugated on the outside, then typically there's a linker involved. There also be stabilizers, in particular polyethylene glycol, targeting moiety, which the last speaker talked about. So there's a very complicated process, of course, which is part of the reason why few of them really have been moved to the clinic yet. The polymers that can be used for the nanoparticles can either be naturally derived or synthetic. There are some advantages and disadvantages of both. The disadvantage of the naturally derived is that we tend to have less control over their mechanical properties and their chemical properties because they're derived from nature, batch-to-batch inconsistency. This one here, probably not such a major concern. They tend to be more costly. The synthetic polymers, on the other hand, probably more practical for large scale-up production and reproducibility. The polymers can be designed with chemical functional groups that we can take advantage of those for attaching either targeting moieties or imaging agents or drugs. But they tend to release acidic degradation products, which, if they degrade too fast, could cause localized tissue damage. They tend to have, lose their mechanical properties if that's important. For drug delivery, it may not be as important for nanoparticle drug delivery anyway. Toxic substances tend to be used in the synthesis process, and that does have to be removed. This is just not a complete list, but a partial list of some of the available natural and synthetic polymers that are available for drug delivery applications for either nanoparticles, microparticles, or patches. And all of these have been described in the literature. For nanoparticle formulation, I want to talk just a couple minutes about that. In the synthesis process, they can be generated from monomers which would require a secondary polymerization to create the polymers from the monomers, or directly from preformed polymers, generally by solvent evaporation, nanoprecipitation, solvent extraction. My group primarily uses the solvent evaporation method. And the various methods for generating nanoparticles was reviewed by Christine Walther in 2009. A really excellent review article that really very carefully goes through all of the different methods, advantages and disadvantages. So for the solvent evaporation technique, which is probably the most simple technique, which is probably why my lab uses it, because I like to do things simple, start out with organic phase and an aqueous phase. And of course, the choice of the method depends on the solubility, the chemical properties, physical chemical properties of the polymer and the drug so that they match. If the drug or even an imaging agent is going to be incorporated into the nanoparticle, then generally they will be added at this phase. This generates an emulsion, and then the solvent is extracted to generate the nanoparticles. So we could either add the drug and the imaging moiety either at this stage when we're generating the emulsion, or at this stage after the particles are formed. For optical imaging, either one would be appropriate, although we can tend to get more of the imaging agent incorporated if we add it at this step. For something like nuclear imaging, it would be very impractical to add it at this step because the time it takes for the generation of the nanoparticles for all the clinical PET SPECT agents, the half-lives are low enough that we wouldn't have anything left by the time we get down here. So those would be generated at this step. Again, the choice between whether it's a single emulsion or a double emulsion would depend on the characteristic of the polymer and the characteristic of the drugs that are being incorporated or attached. So all of those are very important. The process for production, and I have on here for indocyanine green and doxorubicin PLGA nanoparticles, because that's one of the things that we had worked on in our lab. We add the drugs, generate the emulsion, evaporate the solvent, which results in nanoparticles. We centrifuge to concentrate the nanoparticles, wash them to try to get as much of the solvent, particularly if PVE was used as a stabilizer because it has high toxicity, and then we lyophilize them for later use. If we're going to label them with either an imaging agent or a targeting moiety, we would do that, reconstitute them and do that at that stage. Most of our work has been with, for instance, here I'm going to talk about indocyanine green and some other imaging agents. Most of our work has been in incorporating the imaging agents into the drug at this point, and our work is focused primarily on combining imaging and therapy, so-called Theranostics, that I'm sure many of you have heard and are familiar with. This is what the particles look like, at least for the solvent evaporation method. They're about 100 nanometers in diameter, 100 and 120 nanometers in diameter, mostly very small particles, but you also do get a lot of large particles. These large particles can be removed by centrifugation because the large particles will settle. And of course, they're small in number. They look like they're a lot, but they're small in number compared to the smaller particles. If we look at the characterization of them by dynamic light scattering, I have three different examples here. These are bare PLGA nanoparticles, and you see that they're about 106, these particular ones are 160 nanometers. But if, in a small polydispersity index, when we add an antibody to them, antibody conjugation for targeting, the size, of course, increases because the targeting moiety is on the outside of the particle, so the size increases quite a bit. But the zeta potential decreases quite a bit more towards normal, which is more, towards neutral, which is more compatible with uptake and not being scavenged by the RES. But the polydispersity also increases. By adding drug, if we compare this group to this group, by adding drug into the nanoparticles, really didn't change the size or the polydispersity or the zeta potential. But we have to be careful when we attach these targeting moieties to them, because they really do change the nanoparticle. They change the size and they change the zeta potential. Okay, so into the imaging, which is what my talk is all about. Back to the concentrating now just on the imaging. This slide, everybody's seen examples of this slide many, many times, and it just shows why the near infrared is so important, and an excellent talk this morning on the resolution and sensitivity of different imaging modalities. So I'm not going to repeat those advantages of optical imaging compared to other modalities here, but here are some examples of some cyanine fluorophores, which have been investigated in the literature, and the cyanine fluorophores are really the most looked at, the most evaluated fluorophores for near-infrared imaging. Indocyanine green has been approved for many, many years for clinical use in liver image, to diagnose liver function and also cardiac output. I'm going to show later on, compare the ICG to some stuff we're doing with IR820, the the Psi chemicals, the IRDyes. So there are many molecules that have been described in the literature, and this is out of a very nice review article in Theranostics. There are many companies that are producing near-infrared fluorophores. Some of them, like for HW Sands, these are really not intended for biological applications, although I suppose they could be, but they're really more industrial type of applications. Some from like Thermoscientific and Sigma Aldrich, these are really intended for development of in vitro diagnostics like ELISA kits and things like that. But some other companies are developing tracers that are being used in preclinical small animal studies. LI-COR is the only company that I'm aware of that is trying to push their dyes into clinical, but maybe the other ones are. I'm not really that familiar. Here I just want to show as an example of some of the chemicals, the near-infrared dyes from LI-COR, and I don't have any financial interest in LI-COR. I actually don't even use much of their dyes, so I'm not trying to sell LI-COR here. I'm just showing it as an example of all of the different things that we could do with these particular dyes to measure for instance, bone uptake, to measure EGF receptor, to measure CD44. So lots of different applications, lots of different probes are available for looking at different processes, molecular processes. This is a molecular imaging meeting. These are all to investigate molecular processes, primarily in preclinical studies, because as a speaker discussed this morning, the difficulties with moving optical imaging into the clinic. Here, I just want to point out, again, some additional molecules with different chemical groups on them so that they can be attached to drugs or attached to nanoparticles. And then this just describes for the different compounds that they have developed what the imaging applications are. So again, I'm not trying to promote LI-COR here, just to give an example and to help everyone appreciate the fact that there really are a lot of tracers out there that can help you in studying biochemical processes, especially in mice. Larson group I took this from one of their that group's review articles, and the idea is taking water-soluble polymers, so instead of nanoparticles, polymers, and attaching different things to the polymers, for instance, for targeting drugs. What they didn't show on here is the potential for attach imaging agents also for theranostics. So, as I said, not just nanoparticles, but also polymers themselves. And here are just an example of some polyethylene glycol polymers that with active groups on them that can be used to attach an imaging element to them to turn these into imaging agents. And so I'm going to talk briefly about using the amine, polyethylene glycol amine, actually a diamine, in my own study. And as I said before, one of the things that myself and a lot of others are looking at are alternatives to indocyanine green, because indocyanine green, even though it's really the most looked at near-infrared fluorophore because it's been can be used in the clinic, but it is very unstable in aqueous solutions. It has very low plasma resonance time. So we were comparing it to another compound, indocyanine green, and the only difference between the two is this chloro group, this ring here with the chloro on it, which gives it some stability to make that. Increases its stability, but we can also take advantage of this group here for some binding, which is much more difficult for ICG. And so we did some of this in rats, and we did degradation. Half-life, the degradation time is twice that of ICG, which gives us, and also plasma half-life was much longer, hours, compared to only minutes for ICG, which allows more time for the uptake of the chemical into a tumor, if that's the application. So we generated some IR820 PEG diamine ionic nanocomplexes. These are about 50 nanometers in diameter, but they're not really spheres. They're irregularly shaped particles. And they were about 50 nanometers, zeta potential about normal. And we looked at them for cell imaging and also for animal imaging. So we compared the IR820 PEG diamine in 3 different cell lines: a uterine cell line that has MDR, multi-drug resistance, a ovarian cell line that has a HER2 receptor positive, and then a meso, which is a uterine cancer cell line that doesn't have MDR. What we saw was that the nanoparticles, as expected, the nanoparticles increased the uptake in the multi-drug resistant cells compared to the non-drug resistant cells. Compared to the dye all by itself, not with the nanoparticles, but there was no effect in the cells that didn't express the multi-drug resistance. And in the SCOV3 cells, we saw an increased uptake in the SCOV3 cells. We're not sure exactly why that is, except probably due to an interaction of the polyethylene glycol with the membrane increase in the uptake. And we also saw a slower clearance for the IR820 PEG diamine complex compared to the IR820 by itself, and much greater than the ICG, which has an extremely fast clearance, extremely slow, fast plasma clearance time. Okay, well then we also injected, when we injected them into the mice, we looked at the uptake into various organs. These are actually organs that have been explanted, so after 24 hours after injection, we remove the, euthanize the animal and remove them, and we see that the ICG, there's very little activity left because it's all been degraded or excreted. whereas for the IR820 PEG diamine and the IR820 by itself, there's still a lot of activity still in those organs. The distribution was a little bit different for the IR820 than the IR820 PEG diamine. For the IR820, a lot of it ended up in the lungs and more of it into the kidneys. Okay, we also looked at IR820 chitosan conjugates. So here's an example of that. We looked at those in scald 3 cells, and we saw that the chitosan conjugate had a much greater uptake than the IR820 by itself. And if we looked at imaging, this is an example just of 3 different images of the IR820 chitosan, or 3 different animals at 45 minutes after injection. So we get, it really all went to the liver, which is we expected because these were not targeted. There's no tumors in these animals, so we expect everything to go to the liver. But very bright images. And at 24 hours, we see it in the intestines and even in the feces. So it appeared to be excreted intact, so it wasn't degraded in the animal. Next thing I want to talk about is conjugated polymers, and this is a collaboration I'm doing with one of my friends in chemistry and biochemistry. So he lent me some of these slides. These conjugated polymers can be generated to be fluorescent, and the fluorescent is dependent on different reactive groups that are placed into the backbone of the conjugated polymer. So here is an example that that he is working on conjugated polymer particles, and these are these particles. They're very small. They're about 20 to 30, 50 microns in diameter, and they appear to be taken up by the lysosomal uptake. But the important thing here is that if we compare the intensity over time of these conjugated nanoparticles, they're much more stable than FITC, which is a standard dye, fluorescent dye used for microscopy imaging. These can also be used for 2-photon imaging, and a speaker this morning talked about 2-photon imaging, so I'm not going to go into the physics here of that, except just to point out that the 2-photon imaging, an advantage of it, one advantage is that the excitation wavelength can be in the near infrared range, but the disadvantage is that the emission is still in the visible range. So these might be at 700 or 800, but the emission is still about 500 or 600. So you can get the light in to excite the fluorophore, but the light coming back out can be an issue. And also, it's the advantage that you get this bright image from the focal plane is a disadvantage when you're trying to get a 3-dimensional image from an animal. So that's kind of a problem. But we looked at the nanoparticles, these conjugated nanoparticles versus quantum dots and fluorescein over different wavelengths. And we also looked at the conjugated nanoparticles versus quantum dots over time, showing that they're both very stable. So I talked about fluorescent nanoparticles. I talked about polymers, conjugated polymers, fluorescent polymers. And next I want to talk about semi-conductor quantum dots, which I don't use. I'm not an expert in quantum dots to any at all, but just kind of briefly, because this is a very important particle for optical imaging. And I'm not going to go into the physics of it, but if we look at the size relative to to other biological entities, we see that they're in the the 10 to 40 nanometer range. So very nice range where we like them to be for nanoparticle applications for imaging drug delivery. The fluorescence of them is very size dependent, but still in that fairly narrow range where they can be very useful for drug delivery and for imaging. This is a nice review which compared the quantum dots with organic dyes. So before I was primarily talking about organic dyes, so quantum dots compared to organic dyes. The quantum dots a very broad spectrum versus a more narrow spectrum for organic dyes. Excitation, emission is more broad compared to quantum dots, which the emission spectra is a little bit more narrow. A lot of photo bleaching threshold. So this is a little bit confusing because organic dyes are much more prone to photo bleach than quantum dots are, and so that's why one of the reasons why quantum dots are so valuable. Slower decay time, much higher quantum yield, much higher absorbance cross section, and saturation intensity. So purely from an imaging standpoint, quantum dots are an excellent choice for molecular imaging. The problem is they're toxic. And of course, a lot of people are developing new quantum dots, nanocrystals that with reduced toxicity. Again, this isn't really my area, so I'm not familiar with all the literature in that respect. But they're generated by adding the cadmium mostly, although as I said, there are other semiconductors that can be used, but adding cadmium at a particular temperature, and the longer that the soup cooks, the particles increase in size. So you pull the particles out at different times, you get your different sizes. And so, for instance, you'll have these cadmium cellulide quantum dots. Then you wrap them with, they become a core, then you wrap them in a shell, which not only protects them, makes them less toxic, but also allows them to be soluble in water, otherwise they couldn't really be used. So that's really the key here, is that they have to be encapsulated, or they have to be coated, otherwise they can't, they won't go into solution. But the big problem is what happens with this cadmium. It's toxic, and eventually it's going to be causing us problems. Here's just a picture of what they look like, and they also can be functionalized. This is a pretty picture. I'm not really sure exactly what it means. I just borrowed it from Wikipedia, but it's a really nice picture showing that there are lots of opportunities for conjugating things to these particles so that they can be targeted, so that they can be made stealth, they can carry drugs, things like that. And another nice review article which describes some of the more recent advances in different types of quantum dots that are being developed. So really exciting, particularly for microscopy and for preclinical work. I really have grave doubts that the quantum dots will move into the clinic, but again, I'm not working in the area, so I can't really say. So with that, I'd like to thank you for your attention.